All right, so my name is Ben. I'm a third-year PhD student here at Northeastern, and I study natural language processing specifically, which is the subdiscipline of artificial intelligence that studies how do we teach computers to use human language. And so today we're going to work through just a basic example of how you would implement just an off-the-shelf machine learning algorithm in Python using some of the really popular libraries. So this is just going to be beginning to end, everything you need to know to just take a first pass at getting something running. Our plans for the next 3 weeks, the next workshop would be focusing on how to process the inputs, what you need to consider when generating features, how you need to sanitize and clean your data, what are the things you should be looking at in order to get the most out of the inputs to your algorithm. The week after that would be when you're training a model, what are the things you need to consider? How do you select parameters? How do you optimize things? How do you use model selection? What family of models should you be looking at? And then the final week would be what you do with your outputs once you run a model. So there's things like visualization, investigating parameters, sort of an interpretability of the models themselves. So that's just sort of a quick overview of what we're going to do. And as we're going through this, I've just written up sort of a quick little example in Google Collab. So I've been told that a link was sent around, but if you want to follow along, you can check out this little tiny URL link. And what Google Collab does is Google is nice enough to offer a bunch of virtual machines for anybody who wants to run Python code. And they just set up a little virtual environment for you to run whatever code snippet you want to run. This is the Google Docs of sharing code, which makes it very nice and convenient to run. So we're just going to sort of step through the examples, talk about how you do all the common things you need to do, some of the sort of big pitfalls and gotchas that people get stuck in. And as we're going through this, please don't hesitate to stop me or ask any questions. There's, I think, a wide range of experience levels here. So some things are going to be obvious to some people, but not to other people. And the goal really is just to get everybody up to the same sort of level of, given a data set or a problem you're interested in, you at least know where to start for applying a machine learning model and getting some sort of answer at the end. So if you'd like to follow along, go ahead and pop it open. And you should have the option of opening it in sandbox mode. You should have a little button in your top bar here, and if you open it in sandbox mode, then it lets you go ahead and edit your own local copy and tinker with things as we go. That's one of the really great ways to get experience with this sort of stuff and figure out the way things actually work, is just try messing with it on your own. While we're here, and since you guys are all interested in machine learning, I'm going to plug one more thing about Google Collab. It's like a cool tool that's available. You can manage your notebook settings, and Google goes ahead and provides hardware acceleration. So we've just got kind of a easy little example. We've got 5,000 text messages that we're going to try and learn to identify as spam or not spam. If you have things that are larger data sets or more involved models, you might need something like GPU acceleration. So this is a nice place to sort of run everything in a contained little sandbox environment. So just as a show of hands, who has worked with Python before? Okay, so a decent chunk of you. So I'm not going to go into extensive detail about exactly the syntax and stuff. I encourage you, I'm going to sort of describe what things do and show what the code is and what it does. But if you have specific questions about syntax, there are lots of great resources on the internet. Again, if there's something that just doesn't make any sense to you, please ask me. I think it's easier to ask a question and get straightened out right at the beginning than it is to be confused for the whole thing. And the goal here, again, is really to make sure everybody is capable of writing something like this over. Okay, and we're off. Any questions before we get started? Okay, so why would you want to use Python for your machine learning problem? The short answer, as well as what everybody does, and can everybody be wrong? But really, so Python is, I think, the most popular language for just running machine learning tasks. And that's a combination of a couple things. One, it's a very friendly programming language. The syntax is nice and easy. It's not very verbose. It's easy to run. It's an interpreted language, so you get to sort of interactively work on your code, which makes it really nice. And one of the other perks of it is that it's wildly popular. And since it's wildly popular, that means people have written libraries to do all the things that you probably want to do. So less time reinventing the world and more time working on the problem. All right, so on the topic of nice libraries that are provided for us, today we're going to make heavy use of two libraries that you'll see over and over again in any sort of data processing. The first is sklearn, scikit-learn, which implements basically any off-the-shelf machine learning algorithm you're interested in. If any of you have taken like a machine learning class, you'll have learned a long list of things like logistic regressions, linear regressions, decision trees. Anything you can think of that would be on this list, sklearn has like a nice little package for you to just yank right off their shelf and run it, and makes your life really easy. You don't need to implement any of the math yourself. And the second library, or module as they're called in Python, they're going to leverage is called Pandas. And what Pandas is a data management module. So it's going to make it very convenient for us to load our data, to manipulate it, to add to it, and to do all the things we need to do to it before we can actually shuffle it into a model. So in the Collab, the first couple of things we have here, these are just some things to make the output look nice. We're going to suppress a couple warnings that nobody really cares about, and we're going to make sure that we can actually see all the output we want to see. So the primary object that one manipulates with Pandas is called a data frame, which is basically just a way of representing your data set. So Pandas provides this read CSV function, where CSV is a comma-separated value file. This is one of the very common data formats you'll see. You'll have basically all of your data in a big text file separated by commas. And when you get your hands on one of these, Pandas just lets you read it straight into one of their data frames. So the data set we're going to be working with here is a span data set, as I mentioned, where we have 5,000 text messages, and we're going to try and figure out which of these are spam. So there's a copy of this data set that I have posted on my public GitHub, and Google Colab lets us run a text block, which will go ahead and we'll use the wget utility to go ahead and just pull this data file into the local environment so we can access it with our Python. So when we go ahead and read this file, here we see we have span.csv, our local environment. We can go ahead and use the read CSV function of the Pandas module and assign it to our data frame. And then one of the first functions that we have for taking a look at the data object we have is the head, which says just show me what the top of the file is. So if we run this, we'll load our data, go ahead and take a peek at the head. Okay, and we see that we have, so here we see the first few rows of our data set. And on the far left, this is the index, just for bookkeeping purposes. Then we see all our columns across the top. We have a column V1, which looks like if it's ham, meaty content, or spam, things we don't really care about. There's a V2 column that looks like it has all the text content in it. And then there are a bunch of other kind of weird columns at the end that look like they're mostly full of NaN values. This is something that you'll see a lot, is that your data doesn't exactly come all neatly packaged and ready for use. So we have an idea that we have a bunch of kind of weird columns at the end. We're not sure exactly what they are. Pandas also provides a describe function. So let's just go ahead and get a little more complete descriptions of each of the columns of our data. And so here, we see this V1 column has two different values in it. There's 5,500 of them, and the two different values we can see up here are the ham and spam. So this is exactly what we think it is. Additionally, we see that ham is the most common data value, and it clocks in at 4,800 of these. So we see that our data set is mostly ham, with just 700 spam messages. We have an imbalance in our data set, and that's something we should keep in mind as we move forward. Our V2 looks like it's got a bunch of different values. You see some of them are repeated. Sorry, I'll later seems to be the most popular text message sent in this data set with 30 unique instances. Then we see these unnamed 2, 3, and 4 columns. We see that there are only a handful of things in these columns. And our best guess here is that something went wrong when we were reading the CSV. The formatting was weird, there was a character where we didn't expect it to be, something got messed up reading the data in. So we're just gonna ignore those last columns and call that our data cleaning step. So before we get started with that, let's talk about how we manipulate data in Pandas. Really, the primary mechanism of Pandas is a bunch of columns just stapled together. So each column is a series, so it's a list or an array or any kind of sequential container you like to think of it as. And then it's a bunch of these just different columns all stapled together. So the primary thing we can do with Pandas is we can access columns by name. So here, if we ask for the V1 element of the data frame, we expect it to look something like this V1 column. And if we run this, sure enough, looks like that's exactly what we got. So every time we see an output from Pandas, we're going to see the index over on the left. This is just this sort of internal bookkeeping. And then here's our content, the hams and spams. We can also kind of reason about this. So instead of just accessing the V1 column, we can kind of perform element-wise operations on it. So we can generate a column that says, okay, show me everywhere that V1 is equal to ham. And we'll get out an array that's the same shape as the previous one, but instead of the ham and spam values, it just gives us sort of this logical array about whether or not something is ham or spam. So this sort of like element-wise access to the columns goes a little bit further. We can call functions on the columns if we want. So if we're interested in, say, how long the text element is, we remember that the text is in the column named V2. And I happen to know that in the string library in Python, there's a function called len. So we can call this function len on all the elements of V2. And that should give us a neat little column called the lengths of the different text elements. If you don't happen to know that the string class in Python has a member method called len, you can define your own functions. So here we can define a function that takes as an input the text and just returns the length of that text. Then we can use the Pandas method apply and apply our function that we've defined to all of the elements in that column. We should see exactly the same thing. So this just gives us a pretty flexible framework for how to reason over the columns in a Pandas data set. If you like your functional programming, you can generate anonymous functions on the fly. These are all different ways to do the same thing. Okay, so now we know how to sort of look at and reason about our data. How we go ahead and use the more robust access operators that Pandas offers. So there are a few main ways that we slice our data and can select sort of subsets of our data in Pandas. The three main methods are locate, LOC, which you access sort of slices of your data using the names. So you'll tell it which rows you want, which columns you want. And you'll do this using the names of the columns or the names of the rows. The other option is integer locate, where instead of giving it the names, you give it the indices. So this looks like sort of normal list slicing or array slicing if you're familiar with it in other languages. And then finally, we just have simply the at operator, which accesses a single value. So this is like just indexing into a data set. Give us whatever is there. So just a few quick little code examples of how this might work. So here, this says, in this data frame, locate. So first we'll select the rows, and this selects the rows from the data frame where V1 is equal to spam. So this is that same logical array that we generated earlier, and we can use that logical array to indicate which rows we'd like to select. And then here we have just the default empty selector for the columns. So this says, give me all of the rows in the data set where V1 is equal to spam and all of the columns for those rows. If you'd like to use something instead of just the default empty selector, here we have V2. So this is instead of giving me all the columns, give me just the text column. And finally, you can make these selectors as arbitrarily complicated as you want. So here we have, give me the rows where V1 is equal to spam and the length of v2, so this is the length of the text, is less than 40 characters. And of those, I only want the text columns. So this is give me all of the short span in the data set. So if we go ahead and run these examples. So here we've selected all of the span in the data set. And here you'll notice this leftmost column, this is that index column. So this isn't an offset into the array. This is the unique ID that was assigned to each of these things. So when we read the data set, each row got assigned an index, and that index is going to be the name, the row name, and it's going to follow it around for the rest of its life. So when we talk about the names of columns, there are these headers, v1, unnamed 4. When we talk about the names of row, it's whatever you have for the index. By default, we just have these integers. You can use whatever you want as an index as long as it's unique. This can be a timestamp or anything you want like that. Okay, and let's make sure we got everything we want. Here's the text of the span. We can see that the index matches up, so we did it, we got it just the span. We can take a look at all the text messages in the span data set. And then here's just the short spans. So it looks like we sort of have a handle on slicing and accessing our data. If you just know the indices, so this is something very common you see in a lot of programming structures, is you know where in the data set the thing is. You say you know that you want a slice of the data, rows from number 5 to number 15. You want to slice the columns 0 to 2. You just use iloc instead. And here we get our slice. And we can see the index follows the things. These are giving me rows 5 through 15, columns 0 through 2. So pretty easy to manipulate. The final thing is this at. So again, at is going to take the names of the thing we want. So it's going to ask us what's the name of the row, what's the name of the column you're interested in. So let's take a look at a slice of the span here. And let's say we want the element that's at row 8, so this is row that's named 8, and a column that's named v2. And so here we see the text we got is this winner, as value, yada, yada, yada. And indeed, up here we see the row is named 8, and the column is named v2. Okay, so now that we know sort of how to manipulate our data set, let's go ahead and use it to clean this up into something that we can actually begin working with. So we don't really know what's going on with unnamed 2, 3, and 4 from the very beginning. They look kind of noisy, kind of messy. There aren't a lot of values in there. It's mostly empty. Let's just go ahead and get rid of them. Easiest thing to do. Later on, if we feel like we want to squeeze a little bit of extra performance out of our thing, we can go back and take a look at the things we got rid of to try and decide if there's anything useful with that. So for now, we're going to use one of the Pandas functions, drop, and just drop those columns. And sort of the idiom here in Pandas, so all of these operators return a new version of your data frame that's updated with whatever your operation is. So here, we're going to take data and drop the columns and then reassign that back to the data we're working with. And then V1, V2 aren't very nice to work with. It might be easy to forget exactly which one's which. Easy to make a typo between V1 and V2. Let's go ahead and name them something a little bit more useful. So Pandas provides a rename function for manipulating the names of column headers. And all we're going to do is create a dictionary and map some values. So we want V1 to be called the label, and V2 to be called the text. So, and then we'll go ahead and apply this rename map. And then the final thing we're going to do is that we currently just have the label column as spam or ham. It's nice to have numbers. Ultimately, we're going to need numbers. Yeah.
Quick question. I haven't worked with Python in a long time. Is it passed by reference or passed by value by default?
So it's kind of neither. In general, it has mutable and immutable types, and it'll try and pass the mutable types by reference. So it kind of passes everything by reference, but because some things are immutable and some things are like kind of objects under the hood, it doesn't always behave exactly like you think it's going to. So we're going to follow the idiom that's provided in Pandas, which is returning the item, and then we're going to reassign that back to the original thing. So this is just sort of a convention we're sticking with to make sure we don't have any confusions about accidentally manipulating a copy instead of the original thing, which is something that's pretty easy to do. And one of the warnings we disabled at the beginning is that Pandas kind of freaks out when you try and modify a copy instead of the original. So the data frame technically is passed by reference. We can manipulate this and directly change the underlying data frame, as long as we're careful to not take slices, which are copies of the data. So in order to avoid all of this headache, we're just going to reassign things as we go. So here we reassign data after we drop the columns, we reassign it after we rename it, and then we're going to return the value so that we can reassign this whole new cleaned up data set. So let's go ahead and call this nice cleanup function we've got from the data we read, and take a look at what we ended up with. So, look at the head here. So we've got 5 rows and 3 columns. And here the hidden middle column is just this text column. So see, we've gone from our original extra columns, gotten rid of them, added this int label column. Everything looks good. We're going to move on with our lives. So once you have your data kind of neatly formatted, you think you've gotten rid of all the junk, you think it's going to play nice with all your subsequent steps, then it's time to start thinking about the modeling that we're going to do. So just a quick show of hands, who's sort of familiar with machine learning or has like run a model or something? Okay. So about half of you. So I'm just going to give you a quick, simplistic description of what it is that we're doing here and why we might want to do it. So all machine learning is pattern recognition, basically. So we're going to try and learn a function that maps whatever the inputs we have are to an output. So this is function in that same mathematical sense that you learned in high school algebra. We're going to have a mathematical operator somewhere in the middle. This can be something as simple as a linear regression, something as complicated as a really deep neural network. They all fundamentally do the same thing. And what that is take an object that we represent somewhere in our input space. So we've got a thing, we're going to represent it mathematically somehow. We haven't decided yet. And we're going to try and represent it in a way that the values for wherever it is in the input space have some sort of meaning about what kind of thing it is. We're trying to embed these objects in space so that we can separate them using a function. So all we need to do is find a way of mathematically representing our objects and embedding them in what we're going to call an input space. And then we need to define a function that's going to learn how to convert from the inputs to the outputs. And here the outputs we're looking for are a 0 or a 1. So this is just a very simple binary classification problem. It's called where we're just trying to predict which of 2 classes the thing might be in. So every machine learning problem you might be interested in or approach kind of reduces to these 2 things. How do you represent your objects initially? What are the meaningful ways we can separate them? And then a function that's sort of a class of mathematical expressions that's just going to convert them. So let's start by working on a meaningful input representation. So before we get started, there's one critical step we're going to make, which is we're going to separate our training and our test data. So since we're trying to learn a function that can predict what the output is based on an input, it's very important that we understand exactly what it is we're trying to achieve. And here our goal is to be able to take something new that we haven't seen before and tell you whether it's ham or spam. The much less interesting task is to take something you've already seen and guess whether it's ham or spam. If you've already seen it, it doesn't matter, you can just memorize what that specific one is. What we're interested here and what makes machine learning a cool field is our ability to generalize to new unseen things. That's sort of the whole problem. So we're going to split off a chunk of our data set and leave that until the very end. And that's what we're going to evaluate our model's performance on. This is very important and a mistake that's very commonly made, because if you sort of make design decisions as you're constructing your model using the test set, then you're going to get really good at predicting the test set, but who knows how good you are at generalizing to new, truly unseen things. So this is where sklearn is going to come in. sklearn does all the sort of machine learning side stuff, and they provide for us a function that just splits our data into train and test data. So here, we're going to split off 30% of the data for the test size, which is a pretty normal thing to do. The amount of data that you need to train a model depends a lot on how hard your task is, what sort of model you're using, and sort of what your output space looks like. Here we have a pretty simple thing. We've got a few thousand text messages, trying to learn if they're ham or spam. We should be able to go ahead and split off 30% without compromising our accuracy. So let's go ahead and split the data. And here we see we've saved 3,900 text messages to train on, and we're going to test on 1,672. All right, now that we've got that out of the way and we have our test data sort of carefully stowed off to the side, we're going to start engineering our model and see if we can actually put something together that will learn how to separate these two. The first thing that we're going to need to do to get started is right now our objects are just text messages. Yeah.
What does that mean?
Oh, yeah. So this is going to shuffle and then split your data. This is what the function does, because oftentimes you'll have a data set where like the first half is class 1 and the second half is class 2. So just to make sure that there's no weirdness in like the way things are ordered in your input, it shuffles the list before it splits it. Since this is a random operation, I kind of want everybody to have the same experience running this, I've fixed the random seed. So it's always going to shuffle it in the same way for everybody. So it's just sort of fix it. So it's still a random order, but everybody gets the same random order. Yeah.
Won't that create an imbalance in the test data? So unequal number of examples for the two classes that we have.
Yeah, so the ratio of like the ratio spam to ham should be about the same in the test and the train, right?
So shuffling it, wouldn't that manage the ratio?
I mean, so if the shuffle is truly random, then we should be able to take whichever chunk we want, and it should sort of roughly have the same distribution as our training data. So all that we really care about here is that our test set should sort of approximate the same distributions as our training set, because that's going to sort of be the situation that we envision ourselves in the wild. Problems aren't always this nice. Sometimes your test set will be systematically different from your training set, and figuring out what to do about a situation like that is a whole nother workshop. So we're just going to shuffle it randomly, assume that things are kind of distributed the same. We're not going to check. If they aren't, oh well, sometimes those kind of things happen, and our life will just be a little bit harder. So we have our training data here. We're going to go ahead and take a look at it and start making decisions about our modeling based on this. So if we select everywhere where the label is spam and look at the top 10 rows there, and look at everything where the label is ham, and look at the top 10 things here, we can take a look at sort of the different text messages we have in a few different classes. So here's all of our spam, here's all of our ham. Since we're looking to represent these messages somewhere, we're looking to embed them in, sort of create a vector that represents them. And we want this vector to capture quantities that have sort of something to do with the differences between spam and ham. So just looking at this, we might make a couple sort of quick and easy observations. First, spam looks like it has a lot more numbers in it. There's sort of all sorts of like phone numbers, please call this, call this, call this. It has sort of prices, and it looks like there are a bunch of numbers in here. Something else is that there are lots of capital words in the spam. Big brother alert. Also, these things don't really show up in that ham quite as much, so based on this small little sample. the spam messages look like they're a lot longer. Nobody writes essays to their friends in their text messages. You see the text messages are often sort of quick and easy. So we have a few observations about quantitative ways in which these two classes might be different. So let's go ahead and build vector representations for our objects. So you remember from that example where we defined a function and looked at the length of each text message, we're going to do something similar where we're going to define functions that compute each of these quantities that we might be interested in. So the first thing we're going to look at is how many numbers are in each of these text messages. And so these are going to be functions that take as an input the whole row and return whatever we want that feature value to be. So these quantities are what we're going to call the features of our model. These are the things that we're going to use to make decisions, and they're what are going to be the inputs to the mathematical function. So if we quantify the quantity of numbers, the quantity of uppercase letters, and then the length, that'll give us a point somewhere in three-dimensional space. And our hope is that if we throw all of these messages up into the three-dimensional space using these quantities, all the ham tends to be in one place, all the spam tends to be in another place. Things aren't always that simple. There might be multiple clusters. We see that there are lots of long ham messages. Not all ham is short, but maybe those long ones don't have quite as many capital letters in them. So all we're hoping is to be able to embed these somewhere in the space that are such that our function can learn to sort of draw a line between the two different classes. We're looking to create a decision boundary in this feature space that's going to allow us to separate the two classes. So, really simply, we have a function here that's going to loop over each character in the text, the row's text. Remember, we renamed this column to be text. And then we're going to say, okay, if this character is a digit, anything from 0 to 9, just increment the count. And once we've gone through all the text, return that value, and that'll be the feature's value. We're going to do the same thing for counting uppercase characters. If anybody's sort of thinking about this, maybe the number of individual characters isn't exactly the sort of number thing we're interested in. Maybe we're more interested in things that look like phone numbers. Or maybe we want like a compound number, 6,000, to really count as just one number. So lots of different ways you might implement something even as simple as count the numbers. But this is the quickest and easiest thing, and we're going to see how it does. We're going to do the same thing with uppers. Maybe what we're not really interested in is how many characters are uppercase. So we might be more interested in something like a percentage of characters are uppercase, or something like how many words are completely uppercase. So this is the quick and easy thing. It might not be quite exactly what we want. There might be a more informative way to do this. But always start with a simple thing, see if it works, and improve from there. So what we're going to do is generate additional series for each of these things. So this will be new columns. Remember at the beginning, we talked about Pandas data frames basically being a bunch of columns stapled together. That means it's really easy to compute more columns and just stick them onto the end of your data set. So here, we're going to create an add features function that takes our data frame, and it's going to add 3 new columns for each of these functions we've defined. The first one here is a count numbers function. It's just going to call this function on each of the rows in our data set. And we have an extra little argument here, which is the axis, which is, should it be stepping over the columns in the data set, or should it be iterating over those rows? And here we want to apply this function to each of the rows. And then here, this is exactly that length function that we saw earlier in the example. So we're just going to apply these 3 functions, assign the returning columns to new columns in our data set, and take a look at what we got. So here is our new data set. The original things are the same. We see over at the end, we've appended some new things. The number count, the upper count, and the length. So here, right away, we can see, here's a spam message in our data set. And it looks like, just based on these features we've added, it looks like kind of an outlier. It has a lot of numbers in it, and nothing else does. This first spam message also looks like a little bit of an outlier. It has 13 upper counts. Nothing else really has that many. So these features don't look too bad based on the 2 examples we've seen in our data set. We have reason to sort of think it might work and proceed with actually trying to train the model. So, like I've been getting at, what these models do is they take numerical inputs. So we're going to have a vector or a list or any sort of sequence of numerical values that represent our inputs, and it's going to learn a numerical output. So we have a big data set here. We need to split out our numerical inputs and our numerical output. And then we're going to tell Python to learn how to go from one to the other. So here, our numerical outputs are just this int label column we created earlier. And our numerical inputs are going to be number count, upper count, and length, the features we computed. So the naming conventions here, the outputs are the y, the inputs are the x. This is the same as high school algebra. You learn functions from x to y, not a coincidence. So let's go ahead and split them up and make sure that we got everything right. So looking at the top of our x data frame here, we see we have just the numbers, perfect. Looking at the top of the y data frame, we have just the outputs. Looks great. Something else that we did while we were at it is went ahead and added the features to and split up the test data too. Because now we're done monkeying with data, we're done engineering everything. All we're going to do is train the model and then evaluate it on the test data. So when it comes to training a model, we can sort of dip into sklearn's big bag O models. There are lots of different types of problem you might be interested in. There are regression problems where you're trying to learn a mapping from your input to a continuous value. So this is given facts about a person, how much money are they going to make? Given facts about a place, how much does rent cost? Any sort of like continuous mapping problem. Here, we have a classification problem where our output space is going to be between 0 and 1. We're trying to learn probabilities. What are the chances this message is spam? What are the chances it's ham? So, from the class of models that learn probabilities, logistic regression is a great place to start. I'm not going to go into a lot of detail about exactly what logistic regression does. As far as actually training one of these models, in order to get it running, you don't even need to know that much. You can read through the document for every model you might be interested in. So here sklearn has a great documentation. It's going to talk about all the things that go into it, all the things you might be able to tweak, anything you might need to know about running it. But as far as actually implementing it goes, sklearn makes it really, really easy. All we're going to do is say we want the linear model module from sklearn, and then the model we're going to run is a logistic regression, and we're going to instantiate the logistic regression. And once we have our default logistic regression, all we have to do is feed it the inputs and the outputs. And it'll learn all of the internal parameters. These are things like coefficients for the different features we've learned. It's going to learn how to use that input to best reconstruct the output. So we can go ahead and run this code. And that's it. We just trained a model. It's really that easy. Let's see if it preserves my... Perfect. Okay, so we picked our model, logistic regression, because somebody said it was a good place to start. Let's take a look at how it did. So sklearn also provides kind of the tools we'll need for investigating the outputs of our model. So the predictions here are going to be, we're going to give it those test inputs, and it's going to tell us what it thinks the outputs for those inputs should be. Go ahead and see how it does. So we're going to go ahead and here and use their accuracy score function and give it the true values, which are the test values here, and then our prediction, and it's going to tell us how accurate we are. And here, accuracy 98%. That seems pretty good. Something to be concerned about here, though, is that accuracy is sometimes misleading. If we remember, our data set was mostly ham. So it's important to sort of, when you're evaluating something like accuracy, if you have a huge imbalance in your data set, if say 99.9% of the things are negative and only very rarely is it positive, and all you're evaluating with is accuracy, it's very easy to get 99.9% accuracy if you just always say negative. So, as a baseline, let's take a look at the accuracy of just guessing the majority class. Here that's 87%. So, looks like we did actually learn a pretty substantial amount how to separate spam from ham. The sort of imbalance in the data set hints at a couple other things we might want to measure when you're evaluating your model. A couple other popular metrics are precision and recall. So here precision says, this is of the things that I called spam, how precise was I? How often was I right when I said something spam? 96% of the time when something was spam, I said it was spam. That's pretty good. Only occasionally did I accidentally flag ham as spam. Something else that you might be interested in is the recall of a model, which is of the things I was supposed to catch, how often did I catch them? So here, again, we can just boot up the sklearn recall score function, and it tells us our recall is only 86%. So we see that we tended to predict ham a little bit too much, and we actually missed a bunch of spam. 14% of the spam messages actually made it into the user's inbox. So here you can kind of see that there's a trade-off between these two things. The more strict you are about calling something spam, you need to be like 99% sure something's spam before you're willing to call it spam. Your precision is going to be really good, but you're going to let stuff go that if you were only 70% sure it was spam, if you let that go, your recall is going to go down. So these are other things to think about when you're training models. What exactly is it that you're trying to optimize? And here, let's just take a quick look at some of the outputs from our model. So here's something we can do. This is a Pythonic thing where we have a bunch of sequences. They're all the same length. And we're just going to zip them all together so we can step through them one at a time. So we're going to zip up the text labels, or predicted labels, and the actual text values for those things. And we're going to look for everywhere that the true label didn't match what we predicted. And we can take a look at every mistake we made. So here, this is on the test set. These are the mistakes we made. So here's something that we predicted was ham, but was actually spam. This looks pretty convincing. It looks like most of the time, the mistakes we made, they were actually spam. We called them ham and let them into the inbox. So we can look at this and sort of get a feel for what sort of things did we let through by mistake. Something else we might be interested in is of the things that we let through by mistake. So here, this is the same true predicted labels that we saw before, but something we're going to ask our model for. This is something that all of the probability classifiers from sklearn provide, is what are so this is give me instead of just what did we think it was, what did we think the probability that it was ham versus the probability that it was spam. And we can look for everything where those probabilities are like pretty close together. And these are the cases where the model wasn't very sure. These are the things that were close to the decision boundary. We might be interested in things that are close to the decision boundary because it's easier to move the outputs of a function a little bit than it is to move them a lot. So these might be easy wins for us if we can find some way of sort of capturing these mistakes. We can sort of look at our outputs, look at the mistakes we made, revisit our model, maybe add additional features, tweak the way we do things, and try and bump up our performance a little bit. And there's a gotcha here, which is now we're looking at our test set and making decisions based on our test set, which I told everybody not to do. And this is the reason why when you split a test set, often what you'll do is split off a chunk of that test set to use as development for doing this exact kind of thing. So when you need to make modeling decisions, it's useful to have some data to sort of see where your mistakes are. And then at the very end, once you've really settled on what you want your model to be, what you want your features to be, then you go and evaluate them. So this is our example, start to finish, of how to go from just a pile of text messages with their labels and generate a spam classifier that is 98% inaccurate. So if people have any questions or comments or concerns? please go ahead and let me know. If people want to hang out for a little bit and tinker with the code and try and make some changes, or see if everything works for them, that would be great, and I'll hang around for a little bit and answer questions and help people with it.
Cool. All right. Thank you so much, Ben, for taking the time. Again, another round of applause for that.